Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing high availability, what it means, and features to be used to facilitate a highly available network. In this lesson, we'll review the purpose, configuration, and operation of link aggregation groups and redundant trunk groups. Both of these features enhance the availability of our networks by mitigating the loss of connectivity associated with a link between devices going down. First up, let's go over what a link aggregation group is and the benefits of configuring one. Link aggregation grouping is defined in IEEE 802.3 AD. The standard describes the grouping of multiple physical links into a single logical Layer 2 link. Now, I say Layer 2 because 802.3 AD groups connections at the link layer, or Layer 2 of the OSI model. Link aggregation groups, or LAGs, are often depicted in this manner, shown in the diagram. We'll have multiple links between two devices and the circle around them, indicating it is a link bundle, or LAG. Configuring a LAG between devices has two main benefits. First, links may be added or removed to a LAG without the LAG going down. This means if one of the links are broken or disconnect in some way, the logical connection between the two devices won't go down. This means there will be very minimal impact to traffic flows in the event of a link failure. As I'm sure you can imagine, this can greatly enhance the availability of our network resources. The second major benefit of implementing LAGs is the inherent ability to load balance traffic across all participating links of the group. This load balancing is done by sending a whole frame over a particular link and distributing the frames across all links in the group. The specific physical link that is used to transmit a particular frame is determined by the device hashing the information in the frame's header, and then using the resulting hash to correspond to a particular link. Some device manufacturers only use Layer 2 or Layer 3 information by default. This would mean that all traffic between two MAC addresses, or all traffic between two IP addresses which traverse this LAG, would end up being directed to the same physical link. This can cause very uneven load balancing if most of the traffic is between two servers, for example. Junos will also include Layer 4 information. So, the TCP or UDP source and destination port numbers. This will have a much higher likelihood of evenly distributing the traffic between links, as each flow will end up directed to a particular link. A last item to note is that traffic originating from the Junos device itself will always traverse the lowest interface number in the LAG to its destination. If the LAG consists of GE00, 10, 11, and 12, then traffic originating from the RE will traverse GE0010 always. Excellent. So now that we know what a link aggregation group is, let's move on to the control protocol that allows the devices to dynamically negotiate the addition and deletion of the member links of the LAG. The Link Aggregation Control Protocol, or LACP, is the control protocol which allows the devices on either end of a LAG to dynamically detect one another and to add or remove the member interfaces of a LAG smoothly with minimal impact. LACP works by processing control frames describing information about the LAG. LACP has a concept of active and passive mode. When in active mode, the device will originate LACP control frames. When in passive mode, it will only process and respond to control frames received. It will not originate any of its own. Because of this, if both sides of a lag are configured as passive mode in LACP, then the lag will not negotiate and will not come up. At least one side must be in active mode for the lag to successfully be negotiated. In the diagram below, this concept is illustrated. We have the bundle at the top with both sides being in active mode, and the bundle on the left with one active and one passive. The links at the bottom, however, are not forming a lag because both sides are configured in passive mode. Excellent. Now that we know what a lag is and how LACP helps facilitate the creation of a lag, let's move on to the configuration of LACP and lags. Lags are represented in Junos by aggregate Ethernet interfaces, which use the AE interface naming prefix. By default, no AE interfaces are present on a Junos device. We must configure the chassis to create them. When created, these AE interfaces will have 0 members, until we configure physical interfaces to be a member of the 802.3AD link aggregation group. As we see in the configuration snippet below, prior to configuring the aggregate Ethernet interfaces, when we run show interfaces terse for any AE interfaces, our response is empty. We then use the set chassis aggregated devices Ethernet device count command to create the number of AE interfaces we need. We can create up to 128 AE interfaces, where the index number starts at 0 through 127. In this configuration, we're creating 2 AE interfaces by specifying a device count of 2. Once committed, we see when we issue the show interfaces terse command once more that we now have our AE0 and AE1 interfaces showing. The AE interfaces will remain operationally down until LACP successfully negotiates the lag, as the AE interfaces represent the lag itself. Now that we've created our AE interfaces, let's see how we configure LACP and add member interfaces to the group. Here, at the top, we see that we can configure the AE interface just like any other interface, where we're configuring the Ethernet switching protocol family and the VLAN membership of the interface. LACP is configured under the Aggregated Ether Options configuration hierarchy under the Logical Unit 0 on the AE interface. Here, we're setting the interface to participate in active mode, meaning it will originate LACP control frames in an attempt to form a lag. Member interfaces are added to the lag under the Ether Options configuration hierarchy of the physical interface you wish to add to the lag. The physical interfaces, which are to be members of the lag, must not have any logical configuration, and they must be operating at the same physical speed. Using this command, set interfaces, interface, ether options 802.3AD, we can specify which AE interface the physical interface is to be a member of. As we see in the example output below, once the physical interfaces are added to the lag, the AE interface is now in an up state, because the physical interfaces are also up. As long as at least one of the member interfaces are up, the AE interface will remain up. There exists a configuration option to specify the minimum number of member links that must be up for the AE interface to remain up, though that is outside the scope of the JNCIS ENT. We also see in the show interfaces terse output that the physical member interfaces are showing to be running the AENet protocol family, along with the AE interface they are a member of. Excellent. That's it for the lags and LACP. Let's move on to the last feature, redundant trunk groups. A redundant trunk group, or RTG, is an alternative feature that may be used instead of spanning tree protocol for redundant layer 2 uplinks. RTGs are typically configured at the access layer switches, as shown in the diagram below. We would have an RTG configured with the two uplinks from the access layer switch to the aggregation layer switches. An RTG may only contain up to two uplinks, where one is in a primary active state and the other is in a standby backup state. Spanning tree protocol must also be disabled on these interfaces. If it is not, a commit error will be displayed. RTGs work very similarly to spanning tree in that the redundant link blocks user traffic until it becomes active. Layer 2 control traffic, however, like LACP and LLDP, is still received and processed on the backup link. It's best practice to still run spanning tree protocol on the aggregation switch side of the link, to mitigate any human error potentially causing a forwarding loop. Let's move on to the last slide to see how we configure an RTG. In an RTG, both the primary and backup ports must be members of the same VLANs and participating as the same interface mode, being either a trunk or access port. In the configuration snippet below, we see that a redundant trunk group is configured in the switch options configuration hierarchy. Using the set switch options redundant trunk group and specifying a name of the group, then the member interface. One of the interfaces must be set as the primary interface. This uplink will always be active as the primary as long as it is operationally up, meaning it will preempt the backup. If the backup takes over due to a link failure, once the link failure is fixed, the primary will take back over as the active interface once again. And that's it for lags and RTGs. I appreciate you sticking with me to review the concepts and configurations of these protocols that enhance the availability of our networks. I hope that this lesson has been informative for you, and I would like to thank you for viewing.